Good day, students. This is topic 1, lesson 8, symmetry and sequence of transformations. So in this video, we're going to be looking at 3 main targets for our learning. We're going to be applying 2 or more transformations to a given figure to draw transformed figures. So we're going to be emphasizing on rotation, reflections, dilations, and translations. We're going to specify a sequence of transformations that will carry a figure onto another, and we're also going to describe rotations and reflections that carry a geometric figure onto itself. So some questions we have to ask ourselves is, what rotations will carry a regular polygon onto itself? So any rotation that's centered at the central angle and based on the central angle's measures carry figures onto itself. Also, 360-degree rotations carries figures back onto itself. And second, about which location do you rotate a figure in order to carry it onto itself? Well, we always rotate a figure about the center of the polygon or figure. Okay, example 1 says, draw the image of the figure in the plane after the given combination of transformations. So they give us here triangle ABC, and we are going to go ahead and apply all 3 transformations that we see. So as you can see, we have 1, 2, 3 transformations. So let's look at our first transformation. Our first transformation shows that it is a translation. So it's telling us that our x, we are sliding our pre-image units to the left 1 unit and down 1 unit. So let's start with A. A to the left and down would be here, and that's our A prime. B to the left and down would be here as B prime, and C to the left and down would be here as C prime. And this is our first transformation. So let's go ahead and document those points. A prime we have as 1, 1. B prime we have as 1, 4. And C we have as 2, 1. The second transformation that we see is a dilation. We know it's a dilation because there is some factor being multiplied by the x coordinate. So it's telling us to take all of our x coordinates and multiply that by 3, and our y coordinates remain the same. So we're going to keep all of our y coordinates the same, and we're going to multiply all of our x coordinates by 3. So we have 1 times 3 is 3, 1 times 3 again is 3, and 2 times 3 gives us 6. So let's do this in a different color. We have A double prime at 3, 1, so that would be here. We have B double prime at 3, 4, so that would be here. And we have C double prime at 6, 1, so that would be here. So we have our new transformation, which gives us A double prime, B double prime, C double prime. All right, and then our last transformation we see here is a rotation. This last transformation is a rotation about the origin at 180 degrees. So this transformation tells us that we take our previous units and we're taking the opposites of our x and y. So the opposite of positive 3 is a negative 3, and then the opposite of 1 is a negative 1. And then here we have a negative 3, negative 4, negative 6, and negative 1. So let's try a different color here and plot those points for our last transformation. So here I have a negative 3, negative 1. So we have our first point here. That is A triple prime. B triple prime is negative 3, negative 4. And C triple prime is negative 6, negative 1. So we have A triple prime, B triple prime, and C triple prime. And we can connect all of those points here. And here we are, ladies and gentlemen, we have our image after our 3 transformations. So we originally had our pre-image of A, B, C, and we are ending here with our image A triple prime, B triple prime, C triple prime. All right, we have example 2 where it says triangle QRS is the image of triangle LMN under a sequence of transformations. Can each of the following sequences be used to create the image QRS from the pre-image LMN? So they already tell us that LMN is our pre-image and QRS is our image. So the first sequence that we see is to reflect across the y-axis and then translate along the vector. And we're going to answer yes or no. Yes, it does create a sequence that allows us to map our pre-image onto our image, or no, it does not follow through. It is not a sequence that we can use to map these two images onto each other. So to reflect along the y-axis, remember, definition of a reflection is that I have all of my points in my pre-image equally distant from the reflective line, as is my points in my image. So if we start with M, point M we see is 1 unit away, so M prime is also 1 unit away from the line of reflection. N I see is 1, 2, 3, 4, 5 units away, so N prime, 1, 2, 3, 4, 5 units away here for N prime. L I see is 2 units away, so L prime is going to be 2 units away. And as you see, ladies and gentlemen, we have our first image here. Our first image here. Now the next transformation tells us to translate along the vector 0, -4. So 0 is our x, so we're not traveling horizontally, but -4 is our y. So if I'm moving -4 along the y-axis, that means I'm moving down. So I see here that L corresponds to Q, so that means that if I move from L prime to Q, I should be moving 4 units down. Let's see. 1, 2, 3, 4. Well, that's true for L prime. And I have N corresponds to S, so we should be moving 4 down from N prime to S. 1, 2, 3, 4, and that's true. So is this sequence of transformations allowing us to map these two images onto each other? Well, yes, it is. Let's look at the next set of transformations. So let's go ahead and erase this to try the next one. All right, so the next one states that we have a translation along vector 0, -4, and then reflect across the y-axis. Well, this looks very similar to what we had in letter A. Letter A just had the transformations reversed. The sequence is now reversed. So we need to ask ourselves, does it matter that the sequence is reversed? Does it matter that the translation comes first and then the reflection? Or the reflection comes first and then the translation? Will it map still the pre-image onto the image? Well, yes, it will, ladies and gentlemen. It doesn't matter the sequence, the order of the sequence, as long as the rules within the sequence remain the same. So yes, because a reflection and translation is a rigid transformation, remember it does not change the shape or size of the figures. So let's look at C. Rotating 90 degrees clockwise about the origin, reflecting across the x-axis, and then rotating 90 degrees counterclockwise about the origin. So remember our rules. 90 degrees clockwise means that I am using the same rules as 270 degrees counterclockwise, which says to flip my my coordinate points and my x is opposite. Reflecting across the x-axis all just means that I am going to change the sign of my y, and then rotating 90 degrees counterclockwise means I flip my points, but my y is opposite. So all we're doing is just applying these rules to our pre-image points. So again, our pre-image point for M is -1, 5. Our pre-image point for N is 5, 3. And then for L, we have -2, 2. So we're just going to apply the rules as they come. So let's do the first one. For M prime, N prime, and L prime, it tells us that we're going to flip for 90-degree clockwise. We're going to flip the coordinate points, and our x is going to be opposite. So if I flip them, I got 5, comma, and that would be +1. And then flip again with my x being opposite. So that means I have 3, -5. And then I have flip again. That means I'm going to have 2, +2. So if we wanted to graph this, 5, 1 would be here for M prime. 3, -5 would be down here for N prime. And then 2, 2 would be here for L prime. So that's my first transformation in my sequence. Let's look at the next transformation. So the next transformation tells me that I am reflecting across the x-axis. So my x's stay the same, but my y's are opposite. So for M double prime, N double prime, and L double prime. So x stays the same, so that's 5, -1. I have 3, 5, and 2, -2. So let's go ahead and graph that. 5, -1 would be here for M double prime. N was 3, 5, so 3, 5 would be up here for N double prime, and then L double prime would be 2, -2 down here. So my second transformation looks something like this. Okay, and now we have our last transformation, ladies and gentlemen. So our last transformation would be the SRQ. Hopefully this last transformation brings us back to our image, our QRS. So M corresponds to the R. So that's not prime, it's just R. And then N corresponds to S. And then L corresponds to Q. So hopefully we get the same points that we had before. So if I am applying my counterclockwise rule for 90 degrees rotation, my Y is opposite and my X stays the same after I flip. So if I flip them, I have -1, 5, and then we take the opposite of the Y, so that's going to be positive. For S, I flip them, so I have 5, 3, and our Y becomes negative. And then for Q, I have -2, 2, but our Y now is positive. So if I graph this, I have 1, 5, and I can already see R is not way up here. R is right here, ladies and gentlemen. Okay, so that already tells me that this is clearly a no, because it should have brought me back to R down there. Okay, now let's look at our next set of rules. So let me go ahead and erase this. We can keep the work, but we're going to go ahead and erase on the graph. Okay, so the last one says here that we are rotating 180 degrees about the origin, reflecting across the x, and then translating with a vector of 0, 4. So if we remember our rules, rotating around the origin 180 degrees just takes both of my coordinate points become opposite. And again, reflecting across the x-axis, my x stays the same. and my y becomes opposite, and then the vector already tells us what to do. So we can use the space below for our last sequence. So we're going to start out with the same points, M, N, and L, M being negative 1, 5, N being 5, 3, and L being negative 2, 2. And we're going to apply our first rule. So 180 degrees for M prime. I'm taking both opposite for x and y, so that's going to be 1, negative 5. For N prime, I have negative 5, negative 3. And then for L prime, I have 2, negative 2. So let's go ahead and graph those. 1, negative 5 is here. That's M prime. Negative 5, 3. 1, 2, 3, 4, 5. Negative 3 is here. That's N prime. And then I have 2, negative 2 is here for L prime. So this, ladies and gentlemen, is my figure for the first sequence. So we took our pre-image here and then we just rotated 180 degrees. All right, so now we got to do our second transformation. So our second transformation tells us that we are going to reflect across the x-axis. So that means I have M double prime, N double prime, L double prime. And I reflect over the x-axis. My x's stay the same. So I have 1, and then my y is opposite. So that's 1, 5, negative 5, 3, and 2, 2. So let's go ahead and graph that. 1, 5 gives me here. That's M double prime. And then I have negative 5, 3. Negative 5, 3 is here for N double prime. And then for L double prime, I have 2, 2, which is here. So this is my reflection across the x-axis here. And that's a little off, but that's okay. That's my reflection across my x-axis. Now we have our very last transformation, and that is our vector here, our vector. So it tells me that I am going to take these points, and they should bring me back. They should bring me back to my original points that I have here in the problem. So my x's, I'm not moving, so my x stays the same, but I am going to be moving down, subtracting 4 from my y. So 5 minus 4 gives me 1. My x stays the same. 3 minus 4 gives me a negative 1. My x stays the same. 2 minus 4 gives me a negative 2. So let's see what I get. R, is R at 1, 1? Well, it sure is. There we go. That's R, 1, 1. S, is that negative 5, negative 1? It sure is. There it is. And then Q, is that 2, negative 2? Well, it sure is. 2, negative 2 is here. So is this a sequence that maps the pre-image onto its image? Well, yes, it is. And that is example 2, ladies and gentlemen. So example 3 says, which of the following transformations carries this regular polygon onto itself? So remember, a regular polygon has all equal sides and equal angles. So that means all of these angles here are congruent to each other. So we have congruent angles, and it looks like we have 1, 2, 3, 4, 5, 6, 7, 8. 8 congruent angles, so that is a octagon, and 8 congruent sides. So we have a regular octagon, and we are trying to determine which of these transformations can reflect this polygon back onto itself, meaning that if I folded it along a certain line, if I reflected it along a certain line or flipped it along a certain line, will it fold back onto itself? So let's look at line A. Line A, let's go ahead and highlight. That is here. This is line A. Line A. If I folded this along line A, we want to make sure that our vertices are meeting up with each other as we flip. Right? So let's look at the vertices for these. If I flip along line A, that means that this vertice has to match with the opposite vertice. Okay? It has to match with the opposite vertice. So it has to be a vertice that is not connected to a line segment from this actual vertice. So that means the opposite vertice would be here, right here. However, if I notice, that's fine on this side, but on this side, it's going through an actual side. And my vertices, if I fold it along the side, are actually connected by a segment. So we know A is not going to work. Okay. Let's look at B. Let's look at B. So B is this line here. Let's highlight. B is this line here. So I'm going to highlight that in yellow. Now, if I flipped this this regular octagon along this line B, this line right here B, it's actually not going to flip back onto itself. All it's going to do is create another polygon on the opposite side. So it's not actually transforming or carrying it back onto itself. So that's incorrect. Let's look at line C. So line C we have here. This is line C. So remember, ladies and gentlemen, when we are looking at a transformation that carries a figure back onto itself, especially regular polygons, we are looking at if the vertices, if opposite vertices are matching up with each other after the fold or flip or rotation. So if I look at line C, let's look at this vertex here. This vertex would have to match up with a non-adjacent or a vertex that is cannot be attached by a line segment. So this vertex here would match up with this one. This one would match up with that one. This one would match up with this one. So it looks like we have a candidate. If I folded this along this line, yes, it would carry it back onto itself. It would match up perfectly. So yes, the reflection across line C would carry this regular polygon onto itself. And once again, if I looked at D, D wouldn't work because all D would do is take this polygon and just flip it to the other side. So we know that's incorrect. So D is eliminated. So C here, let's go ahead and highlight it, would be our correct answer. Alright, example 4 states, so consider the trapezoid below and which line will carry the figure onto itself. So once again, we are looking for what line that I can fold this polygon along where the vertices match up evenly. So let's look at x equals 1. X equals 1. So x equals 1 would be here. This is 1 on the x-axis. And that means that we have this line that's going through, the x-axis at 1. So let's look at this. Remember, if I'm reflecting along this line, that means all the points of my trapezoid from vertex to vertex have to be equally distant. So let's look at this vertex here. How many units is it away from the reflection line? Well, let's count. 1, 2, 3, 4. 1, 2, 3, 4, 5. So it is 5 units away. And then if we compare it with this vertex on the opposite side, this one is only 1, 2, 3. So we see that's not even. So we know that x equals 0 is not correct as being the line of reflection. So let's try the next one. We have x equals 2. So x equals 2 once again, is located on the x-axis, and there's a line passing through x equals 2 here. So that means this line looks like this. So we have a line passing through, looking something like that. And remember, the vertices for the polygon have to be equally distanced away from the line of reflection. So let's start with this vertex over here. This vertex is 1, 2, 3, 4 units away. And this vertex is 1, 2, 3, 4 units away as well. Well, we can't be too sure, so let's go ahead and check the bottom vertices. The bottom vertex on the right is 1, 2, 3, 4, 5, 6 units away. And this one is also 1, 2, 3, 4, 5, 6 units away. So that means if I folded vertex to vertex, or vertex to vertex, if I folded it right along this line of reflection, x equals 2 would be a good candidate for the line of reflection. Let's see if it can fold horizontally by checking the other two. Let's get rid of these and check if we can fold along the y-axis. All right, so let's check for y equals 4. So y equals 4 means that I am finding some point on my y-axis at 4, and there is a line going through that point. Well, as you can see, the y equals 4 line is not going to work because all it's going to do is recreate this same shape on the opposite side of the line. So we see that that is not a line of reflection that's going to map or carry this figure back onto itself. And lastly, y equals 6 is here. Once again, a line passing through the y-axis at positive 6. And once again, as we can see, ladies and gentlemen, the vertices do not line up perfectly. Okay, these vertices are slightly off, so we know that y equals 6 again is not a reflection line that we can use to carry this image back onto itself. So as you can see, x equals 2 is our answer for this problem. Okay, last problem, we have example 5. Consider the regular octagon below with center at the origin and a vertex at 4, 0. Describe a rotation that will map this regular octagon onto itself. So once again, when we are talking about regular polygons, that means all the angles in this polygon are congruent, and all of the sides in this polygon are also congruent. So we have congruent sides and congruent angles, and they want us to determine what type of rotation will map this regular polygon onto itself. So let's think about it. If I'm dealing in rotations, we know that a full rotation is 360 degrees. And to determine how many rotations we can get if it's centered at the origin, so remember, we are rotating around this point 0, 0. If it is centered at the origin and we know that there is 360 degrees in a full rotation, we have to take into consideration, well, how many angles do we already have in the polygon? And those amount of angles tells us how many times we can actually rotate the figure. Well, we know it's an octagon, okay? It's an octagon. An octagon means it has 8 sides and 8 angles. So we're going to take this 360 degrees and we're going to divide it by 8 to see how many times we can actually, or how many degrees of rotation we can actually get. So I see here 360 degrees divided by 8 gives me 45. So that means I can get a 45-degree rotation to map this octagon back onto itself. And that actually makes sense because if we look here from our origin, if I draw a line going straight through one of the vertices, if I call this my 0-degree mark, starting here, and I make one rotation, so if I turn this one time around, I notice between this mark 0, it's going halfway in between this first quadrant. Well, halfway between the first quadrant, or any quadrant, is actually going halfway between 0 and 90 degrees. So one quarter of a rotation from 0 to finish off this quadrant is actually 90 degrees. So that makes sense that this would be a 45-degree rotation, and we see that we're moving in the counterclockwise position. So we're actually going half a turn of 90 degrees clockwise. All right, ladies and gentlemen, that's going to do it for lesson 8. Make sure that you are going back to your vocabulary in your warm-up activity, watching those videos, and filling out your vocabulary after watching those videos. And I will see you guys in class virtually soon. Have a great day, guys.